The technique of integration by parts. There we go. When do we use it? We use it when we've got an integral of two functions, but one function's not the derivative of the other. So I can't write it as function times derivative and do a nice substitution. So you've got two functions which look like they're just not related at all. There's the formula. Integral of u to v equals uv minus the integral of v to u. What it actually is the product rule, but in reverse. Okay, so we would have, in the product rule, we would have differentiated the uv, and so you would have got u times the v dx plus v times the u dx, and rearranging that formula, you come up with the integration by parts formula. So how do we choose it? We've got two functions. I want one of them to be the u and the other to be the v. So when I'm looking at it, sort of things I look for. So u is something I'm going to end up having to differentiate. So I want to look at it, and so when I differentiate that function, it makes it simpler. Makes it simpler. Whereas the v is going to be something I have to integrate. Okay, so there are two basic ideas when we're choosing which function to use for the u, which function to use for the v. So something like this, x times the sine of x, neither is the derivative of the other, so I can't go and do a simple substitution. So I said I want to choose u, so that when I differentiate it becomes simpler, and the v would be something I can integrate. Now, x and sine x, I can integrate both of those, but it's the differentiation, I think. Differentiate sine x, you're going to get cos x, which is pretty much the same really, it's just another trig function. Differentiate x, you get 1. That is simpler. So that seems to be the logical way to go. We'll have u equal to x, so du will become dx, dv therefore is sine x, v then is minus cos x. So the integral will be uv plus, uv minus the integral of v to u, but we notice v is negative, so negative times negative gives me a positive. Now all I have to do is integrate cos x, integrate cos, and we get sine. And I've just rearranged it so the positive is at the front, but so there it is, sine x minus x cos x, plus of course a constant. Integral of log x. Now you are looking at that and thinking, hang on, there's only one function there. There's actually two functions. The other function is simply the number 1. So when we've got these things that previously we didn't know how to integrate, maybe we can do it this way, because whilst I don't know how to integrate log x, I do know how to differentiate it. So if I choose u to be log x, differentiate it, I get dx on x, which means dv is 1, integrate 1, we get x. So put that together, uv is x log x minus the integral of v to u, which is the integral of dx. Integrate dx, and we get x. So there it is, x log x minus x. Now, you may recall I said that that's one possibly we just end up memorising anyway, because it does appear, a reasonable amount of times you get an integral of log x. But that's how you get it. If you did forget it was x log x minus x, we'd do it by parts. Let's do a definite one. Remember back in exponentials, all the exponentials we were integrating, conveniently the function out the front was the derivative of the power. Now in this case, it's not. So we've got a situation where we've got two functions multiplied together, but one's not the derivative of the other that I can use. So u I'm going to choose to be x, because when I differentiate that, that'll be simpler, and I can integrate e to the minus 7x. That'll just be minus a 7th e to the minus 7x. So uv, but this is a definite integral, so now I'll put my square brackets in, minus the integral of v to u, so it becomes plus a 7th e to the minus 7x. Now, it's up to you whether you want to work out the first square brackets there now, or you want to leave it to the end. I mean, really your call. What did I do? I left it to the end. So now I've integrated the 1/7 e to the minus 7x, and I get minus 1 on 49 e to the minus 7x. Substitute in 1, minus substitute in 0, and there's an answer. E to the x times cos x. Now this is an interesting one, because if I choose u to be e to the x, when I differentiate it I get e to the x. x, not really simpler. If I choose u to be cos x, differentiated I get minus sin x, not really simpler. All right, well let's try the other criteria. I said it was something that I could integrate. Well, e to the x, yes I can integrate that. Cos x, yes I can integrate that. So it doesn't really matter. Go whichever way you like. Which way did I go? I've gone with u being e to the x. So if u is e to the x, du will also be e to the x. dv becomes cos x, so v is sin x. So uv minus the integral of v to u. Oh dear, look what I've got. E to the x sin x, which is pretty much the same sort of thing that I just have. I've got the same problem. So I'm going to have to do it again. Whatever decision you made in the first one, stick with it in the second one, or you're going to end up in a circular argument and you'll end up with something like 0 equals 0 or something like that. So because in the first one I chose u to be e to the x, for this second one I'll also make u equal e to the x. Du therefore is e to the x dx, but this time dv is sin x, so v will be minus cos x. Okay. So we're going to have uv, but it's minus uv, so minus minus becomes a plus, minus the integral of v du. So we get minus e to the x cos x, and I'm back to where I started from. But now is when I look at this, and I don't look at it as steps of working out, I think of it like it's an equation. So I'm saying the integral of e to the x cos x is equal to e to the x sin x plus e to the x cos x minus the integral of e to the x cos x. So if I move the integral of e to the x cos x to the left hand side, I get two lots of the integral of e to the x cos x. Now I can do it. I just divide by 2 and I've got my answer. So that is the technique we call integration by parts. Some people call it the reverse product rule. But it does crop up, well, in quite a few integrals, I guess, because whenever you've got two functions multiplied together and you can't use a substitution. So you try this idea.